First, maximum likelihood estimation of the spatial probit in Tobit. And just to set the stage, let's start by considering what happens in the classic probit model. So in the classic probit model, the observations are independent, so the likelihood is made up as a product of probabilities, the product of the probability that u of I or sub I is less than the appropriate bound, which is a function of x and beta. And so we can write this as the product pi sub I, from the integral from minus infinity to c sub I for the density of the standard normal. So that's basically a complicated way of writing the cumulative distribution evaluated at Ci. And Ci, again, to be able to use a single notation for both the observed 1 and observed 0 case, which are only different in terms of their sign, we preface x sub I beta divided by sigma I by a new term that is 2 y sub I minus 1. So when y sub I is 1, the result is plus 1. So then we have the condition that u sub I is less than xi beta over sigma I. And if y sub I is 0, then we have a negative. So then we have the condition that u sub I is less than negative x sub I beta divided by sigma I. And in the classic probit, we set the variance equal to 1 for identification purposes. So this is a straightforward product of univariate standard normal probabilities. Okay. In contrast, in the spatial probit, we have to deal with the whole full joint distribution. And the reason for that is the dependence induced by the spatial autocorrelation. So instead of a nice product of univariate densities, we have an evaluation of an n-dimensional multivariate normal density. So it cannot be emphasized enough what a difference this is, because in the standard case we simply deal with univariate densities, which is easy to do. In the spatial case, we're out of luck. We cannot do that anymore. So the full n-dimensional integral needs to be evaluated for all the bounds, the bound for each of the observations, and applied to a multivariate normal random variable with the variance covariance matrix induced by the spatial autoregressive process. So that's this by now familiar I minus lambda w prime I minus lambda w, the whole thing inverted. So this is no longer a product of univariate densities, and it requires explicit multidimensional integration. Now, you may not fully appreciate what this means, but up till recently, it was impossible, even numerically, to evaluate a multidimensional integral of a multivariate distribution for more than a handful of dimensions, like less than 10. So if you have even something like the US counties, you have a 3,000 dimensional multivariate distribution. In essence, there is no way you can evaluate this multidimensional integral. You just can't do it. So keep that in mind as we proceed, because in essence it means there is not going to be an analytical solution. We'll have to approach this by computational means. Now, to set the stage for the two spatial models, let's re-express this in terms of a series of marginal conditions for the error terms at each observation. And here we're going to do something slightly different, and this comes out of the Baron and Weiverberg papers, where instead of the usual 2 y sub I minus 1, they use the reverse, 1 minus 2y sub I. And the reverse is done because they stick to the original inequality condition, and they set the inverse sign as it was in the original expression. Remember, before we used symmetry to flip the signs, we basically have that from the x beta plus u less than greater than 0 condition, we have that minus u is less than xi beta for y sub I equal 1. And then for y sub I equals 0, we have the reverse, that u sub I is less than negative xi beta. So with this new transformation, this new kind of variable, 1 minus 2y sub I, we can set the inequality condition for all cases as v sub I, which is either minus u sub I for I equal 1 and u sub I for I equals 0. V sub I is less than minus 1 minus 2 y sub I x sub I beta. And so again, this is going to be less than x beta for y equal 1 and less than minus x beta, negative x beta for y equals 0. So these are the standard conditions. And now we're going to write this in matrix form because we want to show the difference between this case and the spatial cases. And we want to move to the log likelihood. So if we take all these 1 minus 2 y sub I terms and put them in the diagonal of a matrix, an n by n diagonal matrix, then we can write this whole thing in matrix form as the probability that a vector of random variables v, that's an n-dimensional vector, one for each observation, is less than a vector that is obtained by taking the product of negative this diagonal matrix z. Because it's diagonal, it only multiplies each element in the vector x beta by the proper 1 minus 2 y sub I. So that's just kind of a fancy notation to do something very simple. So we have this inequality between these two vectors. And these are both n by 1 vectors, n-dimensional vectors. So the log likelihood, just like we did in this maximum likelihood for the spatial models, we don't write it as a product, but we write it as the log likelihood of the whole multivariate distribution. So in the notation of Baron and Vijverberg, the log of the likelihood is the log of a using a multivariate standard normal density with the bounds are minus zx beta, the mean is 0, and the variance covariance matrix is an identity matrix I. So it's evaluated at negative zx beta, right? So for the spatial lag model, there are two changes. First of all, we no longer have x beta, but we have from the reduced form I minus rho w inverse x beta. And in their notation, we write this as gamma sub rho x beta. So again, this is a matrix times a vector, so it turns out to be a vector just like before, only it's a little more complicated now, and it contains the parameter rho. That's why we have gamma sub rho. And then for the error term, same thing. We also have this inverse transformation, I minus rho w inverse times the error term, and we write this as gamma sub rho, the error term, because the variance is a function of the rho parameter in the spatial order regression, and the variance is the familiar matrix inverse that we've seen many times before, I minus rho w prime, I minus rho w. So the marginal conditions then are very similar to the ones we had for the classic probit. We again have v, which is this either negative u of I or positive u sub I, less than negative the z again, the diagonal matrix with the 1 minus 2 y sub I on the diagonal, the gamma transform, the inverse matrix x beta. So the full log likelihood then for the multivariate normal distribution has bounds minus z gamma rho x beta. The mean is 0 as before, and the variance covariance matrix is the one we have above with the inverse term. Spatial error probit, slightly different because we no longer have the reduced form. So the bounds are zx beta as before, and the variance covariance matrix is the only distinguishing aspect here. So again, we use the same notation as before, and the error term becomes gamma sub lambda now, because we use lambda as the parameter in the error model, and then the variance covariance matrix is the familiar form. The marginal conditions then are again V, either negative sub I or sub I, less than negative Z x beta, just as in the classic Probit model. No need for the inverse transformation on the x beta. And the log likelihood is again a multivariate normal density evaluated at negative Z x beta. The mean is 0, and the variance covariance matrix is the expression above with the inverse. So the problem with maximum likelihood is that we need to evaluate this multidimensional integral for the multivariate normal distribution. So the idea of the simulation estimator that Baron and Weiverberg introduced is that we're going to transform this multivariate normal distribution into a product of univariate distributions. Univariate distributions because we're going to transform the dependent V sub i's, the dependent random variables, normal random variables, into independent random variables by a transformation. And so after that transformation, we're back in business and can treat each of these as a univariate distribution, which is easy to sample from. And because we can't do it analytically, we use a simulation estimator. So in essence, what that boils down to is that we compute each of these marginal probabilities and then multiply them together to get a joint probability for the joint multivariate distribution, and the log of that is used in a log likelihood function. So we do this many times, r times because it's simulation, and then we take the average over these r times of these log likelihoods that we have computed for each of the draws. So two important principles. One is that we transform the dependent random variable into a series of independent univariate random variables. The second one is that we simulate the joint probability. We simulate a joint probability and then use the average of many simulations as a value in a numerical optimization routine that maximizes for the parameters. So how does this work? First, the transformation. So we're going to use something called the Cholesky decomposition, which is a decomposition of a square matrix into two triangular matrices, a lower triangular and an upper triangular. And actually, they're the same. So this usually is expressed as A prime A, where A is the upper triangular one and A prime is its transpose, which is a lower triangular one. So the product of these two triangular matrices is the full matrix. So what we use this for is to decompose the inverse of the variance matrix. And we'll see in a second, or let me show you why that is. Because if you remember, the variance matrices, omega is actually the inverse of a matrix, right? The inverse of that matrix is an analytical expression. It's identity matrix minus lambda w plus w prime plus lambda squared w prime w. So that's easy to write, much easier than the inverse term. So we decompose that analytical expression, which is a square matrix, and get the Cholesky decomposition. And one of the reasons why we deal with that rather than with the original variance and then invert it is because the inverse of a triangular matrix is a very easy thing. It's much easier than a full matrix. So we avoid the n by n matrix inversion problem. So to make this concrete, if V is the vector, and it's a multivariate random variable, so it's a vector of n observations that has a variance covariance matrix omega, and we decompose omega inverse as A prime A, then if we pre-multiply V by A, we get a standard normal variant. You can see this because the variance of eta is A variance of V times A prime, and the A prime A is the inverse of the variance. So A prime A is the variance, so these two cancel out, and we get the standard normal distribution. So, but the eta variable as such is not useful to us. We need to have V, so we get V back by pre-multiplying eta by A inverse. Now, you might say, why go through this complicated transformation and then get back to something that we pre-multiply by a triangular matrix? Well, the reason for that is that now eta is standard normal, and the B eta is a system of equations of inequalities, actually, not equations, of inequalities with a particular triangular form, and we can actually solve that easily, recursively from going from the bottom to the top. So what are we doing here? We are getting rid of the problem that these V's are all codetermined. They have a multivariate distribution. So we express the V's. We don't replace the V's. We express them differently. We express them as a product of a matrix of constants. These constants, we can treat them as constants, but actually they involve the spatial parameter because they come from the omega inverse, which has a spatial parameter in there. But for our purposes, we can treat them as constants, so we know them. So we can solve this inequality, and then each of these etas can be treated as a univariate random variable. So we can compute its cumulative distribution, just like we did in the standard probit with our phi of x beta. We can do that for each of these, and then multiply all these probabilities together to get the joint likelihood, and the log of that is the log likelihood. So let me show you how this actually works. It's a little bit complex, but once you see the structure, it's actually amazingly straightforward. So the top graph gives you the vector inequality, right? So the vector inequality gives, they change the notation a little bit. So the V on the, this is actually not from the Braun-Weiverberg paper, it's from another paper by Francese, and the other name escapes me, but which is a very nice description of this, actually. It's one of the readings. So in our notation, this is capital V. It's a little bit confusing, possibly. So beta times eta less than the bound. So the bounds are the x betas. So these are the bounds, right? And the bounds are in the notation of Baron-Weiverberg, the minus z, and for the lag model, the gamma sub rho times x beta. Those are the right-hand side terms of the inequality. So the etas, eta 1 through eta n, are the independent standard normal random variables. They each have a univariate distribution. Now, the whole thing, of course, has a multivariate distribution, but it has a particular shape of this triangular matrix that multiplies these. Now, the interesting thing is that at the bottom of the matrix, we have Bnn times eta n is less than Vn. Okay, and that is can be solved, as you see on the bottom graph, as eta n is less than Bnn inverse 1 over Bnn. Bnn is a scalar. This is not a matrix inverse. So it's basically the original bound, the minus z x beta for n divided by Bnn. So that's a number, and we can evaluate the probability that eta n is less than that value. That's in the same way as we do with the cumulative normal distribution in the Probit model. We have a value for xi beta. We evaluate that. We stick it in the cumulative normal, standard normal distribution, and we get a probability value, a p-value. So that's the p-value for the last one. Then we move up one row, and if we look carefully, we see that the row above only involves two terms, the term in eta n minus 1 and the term in eta n. And with a value for eta n in hand, which we only can do because we simulate it, then we can actually solve that next row. So we now simulate an eta n from a truncated normal distribution with a truncation at Vn divided by Bnn. So we can do that too. So then eta is a properly truncated random normal variable, and we stick it in this equation, which now includes V sub n minus 1, which we know, that's the z x beta for n minus 1, the two b terms, the Bn minus 1n and the inverse of B n minus 1 n minus 1 from the diagonal term, we know those are constant, and then the eta n, which we just drew a value from the truncated distribution. So again, this gives us a value, a scalar. We can evaluate the probability that eta n sub n minus 1 is less than this bounds in the usual way with the cumulative standard normal distribution. That gives us a p-value, the second p-value in our series of independent p-values for our joint distribution, right? And then again, we have the bound for eta n minus 1, so we draw a truncated standard normal variate from that, which gives us a value for eta n minus 1 for the next expression. And the one row up depends on 3 etas, but we have them from the draws. So we can again compute the bound, evaluate the probability, and then draw a new truncated variable, and so work our way up all the way to the top of the matrix. So to summarize this, the RIS sampler, and there's some technical aspects to the sampling that I won't delve into. The reason why it's called a recursive importance sampler is a particular way of drawing the random variables, but we won't get into this. So basically, the key is that we work the inequalities from the bottom up. So our goal, to keep in mind, there's really two things going on here. One is that we need to evaluate these univariate probabilities, and we do that with just a standard cumulative standard normal. as long as we have the bounds, the z x beta bounds. But these are going to be a little bit more complicated because they include these eta terms. So the first thing, the first concept is to evaluate the univariate probability for which you need a bound. And the second thing is to get these eta variables, values for those, and we get those by simulating them, by drawing them from a truncated normal distribution. The truncation bound is the same bound that we used to compute the probability. So the bounds are used for two things. One, to compute the probability, and second, to draw a random eta term, which we then plug into the solution of the next one, row up. We get a new bound, we assess the probability, we draw a truncated random variable, that one goes into the row above, again the bound, probability, and so on. So we work our way up from the bottom to the top of the triangle, so to speak, and then we have n univariate p-values, one for each observation. We multiply these together and we have the joint probability. Actually, typically you don't multiply them together because they're all very small values, so you have rounding errors in the computer, so you take the logs and you add them together. But that's the log likelihood of the joint distribution. So then you do this again, and that gives you another set of univariate p-values, which you multiply together to get the joint probability. So then you have two. You do this a total of r times, and you take the average of all these joint probabilities, and that is the value that you plug into the optimization routine to get the next iteration, which then gets you a new set of parameter values, and you repeat the whole process. So the simulated log likelihood approach runs R simulations, and R is typically like 1,000 or even more. For each simulation, you compute this product of probabilities for the univariate standard normals, evaluated at the right bounds, which you have to compute. You get the joint likelihood, you use this in an optimization routine, and you're good to go. Now, this tends to be very slow because for each new value of lambda, the variance-covariance matrix changes, and of course its inverse changes as well, and you have to do the Cholesky decomposition all over again to get your new b's in the triangular matrix, and then you solve this whole process again. So this tends to be very slow. There is no analytical asymptotic variance-covariance matrix, but typically the numerical optimization routine that you use will give that to you automatically as the Hessian, the second partial derivatives used in the optimization routine. So that's the maximum likelihood estimation.